Hi, today I will be explaining the valence bond theory for the molecule sulfur hex iodide. I already went ahead and drew the Lewis structure. So in order to get that, we know that there are 6 iodides, so there will be 6 bonding groups. Sulfur has 6 electrons, iodide has 7. So 7 multiplied by 6 iodides would be 42, plus the 6 would be 48 electrons. All of these are bonding and there are no lone pairs. Now from here, we can go ahead and draw our Vesper diagram. For our Vesper diagram, going back to our Lewis structure, we know that there are 6 electron bonding groups. 6 bonding pairs with no lone pairs will give us an octahedral shape for both the electron geometry and molecular geometry. Here I have drawn already our Vesper diagram, knowing that it was an octahedral shape. This is how an octahedral shape of a Vesper diagram looks like. So here we have our sulfur, the central atom, with 6 bonding iodides. This is a 2D drawing. So the dashes and the bold triangles just represent how it would look like in 3D. For our Vesper diagram, we see that all of the iodides have bonding pairs. There are no lone pairs. So for this molecule, it would be a bonding pair, 2 bonding pair repulsion. Since they all have bonding pairs, it would all equally have 90-degree angles. It is hard to tell in a two-dimensional drawing, but in the next slide I will show a couple of examples of how you can tell how each angle would be 90 degrees. Here I just have a few examples of how the sulfur hex iodide molecule looks like in 3D. First, this one is from the Odyssey Vesper app, which I like because here it tells us 6 pairs with no lone pairs is octahedral, and this is how the octahedral shape looks like. This app also has an option to view the angles. You just start from the central atom to one of the iodides, and each angle, as you can see, from any point of this view would be 90 degrees. So next, I also built the molecule from a model kit that was provided to us. That way it's easier to see also in a 3D shape that you're holding it and you're able to view it from different angles. So when you're holding the model in your hand, you can see from here to here is a right angle, which is 90 degrees. And we call that axial. We can see that from any point of view here and here. That's why all angles are 90 degrees. And here I have another example that comes from the Moles Editor app. And this app can also show you how a contour diagram would look like, which we will be doing in a few moments. The next step is the box diagram. Here I have already set it up. This is how the box diagram looks like for our molecule Si6, sulfur hexaiodide. So we will be focusing on our central atom, which is sulfur. So here we will have sulfur at the ground state, sulfur at the excited state, and then sulfur at the bonded state. Referring to the periodic table, we can find sulfur at 3p. So first we have to start off from 3s, and then we go at 3p, and then we're going to use 3d in order to hybridize and fill in all the parking spaces that we need for our electrons for the molecule. At 3s, sulfur has both electrons, and at 3p it has 4. So we'll go starting from left to right. Here we have our 4 electrons. Now, since we have 6 iodides, we need 6 parking spaces for our hybridization. So we need to figure out which electrons we need to promote. In this case, it'd be easier to promote an electron from 3s up to the d orbital. And the next electron that we would promote would be one from 3p up here to the 3d orbital. So we promoted one electron from 3s and one electron from 3p. This obviously requires energy. So we'll go next and fill in our other boxes for the excited state of sulfur. Here we'll only have one, we'll have 3, and then I already went ahead and filled in the 2 at 3D. Now from the excited state, we have to go to the bonded state. In order to go to the bonded state, we're going to need to hybridize. Now, the hybridization of the central atom, sulfur, is sp3d2, which I put right here, in the middle of both 3p and the 3d orbitals. sp3d2 because there are 6 bonded electron groups. So we're going to hybridize these 6, and then we're going to fill in the rest to bond them together with the 6 iodides. So here we have the 6, which are the 2 from the 3d orbital, the 3 from the 3p, and then the 1 from the 3s. Now next, we're going to bring down our iodide. There are 6, so I'm not going to draw all of the iodides, so I will just draw 1. And this would be iodide times 6. We find iodide looking at our periodic table at 5p. Iodine has 5 electrons. So we'll go 1, 2, 3, 4, 5. Now since we have 6, so we'll have 6 of these, and they can all fill in a parking space here, 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 and so on. I've already filled in the 6. So now we have all of our bonding pairs here at the sp3d2 hybridization of sulfur hex iodide. And all of these bonding pairs are sigma bonding pairs. From here, we are able to now go to our contour diagram. Here I just have a couple examples that I took from the Moles Editor app showing our orbitals for sulfur and then for iodine. Here is the same contour but just an overlapping view. So that way we see how the sp3d2 orbitals overlap with the 5p orbitals from iodine. Going from this state, we now have to draw the contour diagram in the next slide. But of course, not forgetting that this is still an octahedral shape, and that our octahedral shape has 90-degree angles. So I went ahead and already drew the contour diagram for sulfur hexaiodide just in order to save some time. So here we have our sulfur, the central atom, and you can see that I followed the octahedral shape. So here we have our sp3d2 orbitals, which we saw when we hybridized in the slide before this one. And then here we have our 5p orbitals that I drew in gray, which are represented by our iodine atoms. So here we have our 5p, so 6, each representing an iodine bonding with the sp3d2. And these are all sigma bonds. And at 90 degrees. all at 90 degrees in an octahedral shape. This concludes our valence bond theory for our molecule sulfur hexaiodide. Thanks for watching.